When analyzing data, it's often beneficial for us to make a scatter plot, meaning that we create an ordered pair out of each data point and then plot it on a Cartesian plane. This enables us to visualize any patterns and determine whether or not the two quantities are related. If there's a clear relationship, we say that those data points are correlated. So let's take a look at some possible outcomes. Let's say that we have a table of data where the x-coordinate represents time and the y-coordinate represents distance traveled. If we're in a vehicle experiencing some traffic, our rate of speed might vary a little bit, which would cause our data points to not necessarily be collinear. But there's definitely a linear trend here, and therefore we could use a linear model to represent this data because it's generally trending in a linear fashion. As one increases, the other increases. But let's say we're looking at some data representing the height of a frisbee on a windy day. So our horizontal axis would represent time, our vertical axis would represent the corresponding height. The general tendency is that the position of the frisbee is parabolic, but there are some outliers. The wind picks up the frisbee and moves it off the line a little bit. This data is correlated, even though the data points don't fit perfectly onto that quadratic function. Some data, when plotting it, might better be represented by a logarithmic function, while an exponential function might be better to represent data collected from population growth. To discuss the correlation coefficient, let's focus our attention on a linear data set. If the data is generally trending towards being linear, as one increases, the other increases, then we can try to fit a line to the data, creating something that's called the regression line or the line of best fit. If the line is a perfect fit, meaning that every data point is exactly on the line, that can be numerically represented by the correlation coefficient, which is called R. If R is equal to +1, we say that this is a perfect fit. All of the data points are exactly on the line. And when that R value is a +1, that means that the slope of the line is also positive, meaning that as one value increases, the other value also increases. Notice here we get a correlation coefficient of 0.8. When the correlation coefficient is fairly close to 1, but not exactly 1, we say that there's a strong correlation, but not all of the data points are exactly on the line. A positive correlation means, again, that the slope is positive. Generally speaking, as one value increases, the other also increases. In the next example, the data starts to become a little bit more scattered. While it is generally trending up, as one increases, the other increases, most of the data points are not on the line. This is when our correlation coefficient starts to get farther and farther away from 1. Our correlation coefficient here is 0.3. That's not very close to 1, although it is a positive number, which means that the slope of our regression line will be positive. But the regression line is not a great fit for the data, since most of the data points are not on it. And finally, we see a correlation coefficient of 0, meaning that we can't really make any sort of a relationship between these data points. They're totally scattered with no perceivable relationship. Let's look at data that is now negatively correlated, which means that when we find the regression line for each of these data sets, we're going to end up with slopes that are negative. Let's start with the perfect fit. When we find the regression line for this data, all of the data points are going to be exactly on the line, and we can represent that with the correlation coefficient of exactly -1. When the correlation coefficient is exactly -1, it means that the data is a perfect fit, and the fact that the correlation coefficient is negative means that there is a negative correlation or that the slope is negative. Here we have data with the strong correlation, and we see that the correlation coefficient is -0.8. -0.8 is fairly close to -1, indicating a strong relationship. The fact that it's negative means that the slope of the regression line is going to be negative. And in this last example, we have generally trending negative data. As one value increases, the other value decreases, but most of the data is not on the line. So the correlation coefficient is going to have a numerical quantity that's pretty far from 1. But the fact that it's negative means that when we find the line of best fit, that line is going to have a negative slope. But because the numerical value is pretty far from 1, this represents a weak correlation. So to summarize, the correlation coefficient r is going to be somewhere in between positive and negative 1. If r is exactly equal to 1, we say that it's a perfect fit, meaning that all the data is exactly on the line. That's also true if r is equal to negative 1. This will still be a perfect fit. But if our correlation is positive, that means that our regression line will be going up with a positive slope. But if the correlation coefficient is negative, that means our regression line will be going down with a negative slope. If the correlation coefficient is close to either positive or negative 1, that means what we have is a strong correlation. But if the correlation coefficient is not close to 1, meaning that it's actually closer to 0, then this means that the correlation between the two quantities is weak.